LSST Camera Lens Assembly. The LSST Camera Assembly belongs to the Vera C. Rubin Observatory and was completed at SLAC National Accelerator Laboratory in 2024. It uses 3 large fused-silica lenses, and the largest one, L1, is about 1.55 meters across, making it larger than the famous 40-inch Yerkes refractor lens. It is different from a simple telescope objective because it works as part of a wide-field camera system after the light has already been collected by the telescope mirrors. Its importance is that it helps Rubin capture a huge patch of sky in sharp detail for the legacy survey of space and time, which will repeatedly map the southern sky and track changing objects over time. LSST Second Main Lens. The second main lens in the Rubin camera is the middle lens in the 3-lens assembly, built to help shape and correct the light before it reaches the detector. It was made as part of the same SLAC-built camera system, completed in 2024, using fused silica like the other camera lenses. Compared with the giant first lens, it is smaller, but it still plays a critical role in keeping the image flat and well corrected across the very wide field of view. Its importance comes from precision, not size, because the whole survey depends on clean images over an unusually large area of sky. Yerkes Observatory 40-inch refractor objective lens. The Yerkes 40-inch objective lens was created in 1897 for the Yerkes Observatory in Williams Bay, Wisconsin, and it was completed by Alvin Clark and Sons from glass blanks made in Paris. It was the largest telescope lens ever crafted for a refracting telescope, with a 40-inch aperture and a long focal length that made it ideal for detailed visual astronomy. What makes it different is that it is a true refracting objective, so all the light enters through a single large lens rather than reflecting from mirrors. It mattered enormously at the time because it pushed refractor design to its limit and became a landmark instrument in the history of astronomy. Gran Telescopio Canarias Primary Mirror Lens System. The Gran Telescopio Canarias uses a 3-mirror Ritchie-Chrétien optical design rather than a lens-based refractor, and it was developed as a major modern observatory in Spain. The telescope is built around a primary mirror, secondary mirror, and tertiary mirror, with the mirrors working together to send light to different observing stations. Its difference from a lens system is that it gathers and redirects light by reflection, which allows a much larger aperture than a traditional glass lens could practically support. It is important because this kind of mirror system is what makes today's largest ground-based telescopes possible, especially for optical and infrared astronomy. Hobby-Eberle Telescope Primary Mirror Lens System. The Hobby-Eberle telescope is also a mirror-based observatory, using a segmented primary mirror rather than a large lens. It was designed for efficient spectroscopy and large-area sky surveys, and its optical train is built around reflection instead of refraction. That matters because segmented mirrors can be made far larger than a single glass lens, while still collecting and focusing faint light from distant objects. Its importance lies in showing how modern telescopes solve the size problem with mirror engineering rather than with giant lenses. Keck Telescope Primary Mirror Lens System. The Keck telescope uses segmented primary mirrors, not a lens, and that design was a breakthrough in making extremely large ground-based telescopes practical. Built in the 1990s on Mauna Kea, it was among the first major observatories to prove that many precision-aligned mirror segments could act like one enormous surface. Its difference from a lens system is that each segment reflects light, so the telescope can be much larger without the weight and distortion problems of a huge glass lens. It remains important because this approach set the pattern for many later giant observatories. Southern African Large Telescope Primary Mirror Lens System. The Southern African Large Telescope uses a large segmented mirror system rather than a refracting lens. It was designed to collect faint light efficiently for spectroscopy and other observations, with the mirror arrangement allowing a very large collecting area at manageable cost. Compared with a lens-based telescope, it relies on reflection and a fixed altitude design to keep the structure practical. Its importance is that it brought world-class large telescope capability to the Southern Hemisphere. Subaru Telescope. Primary Mirror Lens System. Subaru Telescope uses an 8.2-meter primary mirror and is another example of a modern large reflective telescope. It was built for wide-field imaging and deep sky studies, and its mirror-based design avoids the heavy, fragile limitations of giant lenses. That makes it very different from historic refractors like Yerkes, because the optical power comes from a carefully shaped mirror rather than a large objective lens. It is important because it combines large aperture, high precision, and versatile observing power in one instrument. Boeing-Ocean/Palomar-Schmidt Telescope Lens Mirror System. The Boeing-Ocean telescope at Palomar is a Schmidt telescope, which uses a thin correcting lens at the front and a mirror at the back. It was built in the 1970s as a wide-field survey instrument and later became famous for photographic sky surveys. What makes it different is the lens-mirror combination, which corrects distortions over a very broad field while keeping the main light-collecting power in a mirror. Its importance is that it became one of the classic survey telescopes of the modern era and helped map the sky on a huge scale.